interval?
Three x cubed plus 4x squared plus 7x plus 2.
Okay, because you have x cubed, if we put here anything else but 0, it will take a long time, only because...
I plan to do 0 anyways.
Okay, so, but if you had said, for example, 1 to 2, I'm sorry, of course, closed. If you had said 1 to 2, or let's say 1 to 4, then I would have had xi as 1 plus delta x, I delta x. And then imagine when I have to take this to the third power. Not difficult, but it will take a while. So what is the interval then?
0 to 4.
0 to 4, perfect. So remember when we're asked to find exact area using limit of the Riemann sum. We need 3 preps. Don't start to write the summation and the limit of the summation notation. It will take forever. So let's do the preps first and then put everything together. So what is the first prep?
Find the delta
X. Very good. Delta X is always b minus a over n. B minus a over n subintervals. What is the second prep?
xi.
Yes, xi, which is 0 plus I delta x. So that's why this is not necessary. So I times delta x is nice, 4i over n. And the last one has to be f of xi. So I'm looking at f of x, so I have 3 times xi to the third plus 4 times xi squared plus 7 times xi and plus 2. So don't forget to plug in the 4i over n, the 4i over n, and the 4i over n. We have to simplify this to the fullest and then take it from there. Okay, 4 to the third. Keep my numbers correct, please, just to make sure. I'm gonna get my calculator up there is up, but just in case I say again that 6 times 4 is 64. Okay, so 4 to the third is 64, correct? Don't trust me, please. Times 3, 192. 192 I cubed over n cubed. Is 192 correct? Stop me anytime, okay? Okay, now here we have 4 squared, which is 16. 16 times 4, I think it's 64, I squared over n squared. And plus 28i over n and plus 2. Are my numbers correct, please? Just in case. If you didn't say anything, it's not your fault, of course. I'm assuming that I'm on the right track. Okay, only now I can write the area is exact. Limit as n approaches infinity from the sum from I equals 1 through n. This is the sum of all areas, of all rectangles, base times height plus base times height, etc., etc. So I have 4 over n, which is delta x, and then I have all this ugly thing. Well, it's not ugly, but you know what I mean. A lot of writing. That's what I meant. Plus 64i squared over n squared plus 28i over n and plus 2. Okay. Now, from here on is all algebra till I get to the limit. And then when I apply the limit, I use L'Hopital's rule. So everything from here should be a smooth ride. This does not have I in it. So it's a constant, it goes in front. Of course it's a constant, it's always the same, it's the base of each rectangle. So limit as n approaches infinity, 4 over n. I would like to cut back on writing if possible. I will have the sum of this, but this is a constant. So I'll put it in front, 192 over n cubed and the sum of I cubed. Plus, it's the sum of the second term, but this is a constant. So I will write 64 over n squared, the sum of I squared, plus 28 over n, the sum of I. Always remember, when we get to a constant, you have to write 2, the sum of 1. Let's take a moment and see if you have questions.
Did we not write the n and the I equals 1 over the, I forget what it's called, the summation, just to save time, or?
Oh, no. No, just laziness.
Okay.
It makes no sense without all this. I just got lazy. It makes no sense. Yes?
Is there ever going to be a case where we can factor out a power?
You said something like crossing powers, you mean?
No, like let's say if there's a power that can be factored out.
No, the power you cannot remove the power. I'm not sure. I don't think I heard what your question correctly, Dixon. My apologies. Is it your microphone or I'm losing my hearing?
Can you hear me?
Yes, I think it's better now.
Okay. Yeah. My question was, is there going to be a case where, let's say, if we have a number that can factor everything in the bracket, we have to factor something out of the bracket?
No, not before. I see. Not before you replace these. I don't think so. Unless the function has a common factor. But the function we picked does not have a common factor.
Okay. That was
I have a question as to why did we write +2 with the summation?
Because it's the sum of 2.
Oh.
You have to apply the sum to all terms. And I have 1, 2, 3, 4 terms. I cannot apply the sum to the first 3 and forget to apply the sum to the last.
Okay. And then after that, does that say I or does that say 1?
It says 1.
Okay.
These are the 4 identities. The sum of 1, the sum of I, the sum of I squared, and the sum of I cubed. So this time we picked a function that has a constant, that has I squared, and has I cubed. So we're going to use all identities. Dixon, did I answer your question?
Oh, yes, that's fine.
Yeah, okay. So now we replace this, we replace this, we replace this, and we replace this. This is the easy one. This is n plus 1 over 2. This is the ugly one, n plus 1, 2n plus 1 over 6. And this is this one but squared. So this is n squared, n plus 1 squared over 4. Of course, you don't have to write them on the side because I have to write them inside anyway, so we're going to write the whole thing again. So this is the limit as n approaches infinity, 4 over n. 192 over n cubed times n squared plus 2n plus 1 over 4. So I have this and I have this. Now plus 64 over n squared. All this thing. N, I will multiply these two. 2n squared plus 3n plus 1 divided by 6. So 2n squared plus 2n plus another n and plus 1. So now I have this done, so to speak. And now this plus 28 over n and n plus 1 over 2. And last one plus 2n. So what did just happen in this step? We eliminated all the summation notations using the identities. Okay, now I have to see which would be the least common denominator. I'm going to try and simplify a little bit, but leave the n, right? So one n from here goes away with one n from here. N squared from here with 2 from here. Do not simplify this one because the denominator will still have n in it. Okay, the 6 is the issue. The 6 is the problem because I can't simplify anyway. I can only simplify by 2. And there's still a 3 here, right? So the least common denominator will still be 6 because 192 is 192 divisible by 4. 192, I don't trust my numbers. Yes, it is. So I'm going to simplify. But I still have to multiply by 6. So maybe I should only simplify by 2. I think I should only simplify by 2. So what is this? 96. Okay, so I have 2n in this denominator, but 6n in this denominator, 2n in this denominator, and denominator 1 here. So the least common denominator will be 6n, because I can't do anything. Even if I simplify, I still have 3. And then 3 and 2 and 2, I still need a 6. Okay. As I said, we have some work to do, especially when a cubic function is in the middle. So limit as n approaches infinity 4 over n. So then the least common denominator, so I'm going to put it here because I may not have enough room. Sorry about that. 6n in the denominator. Okay. So this is only 2n, so I need 3 times 96. What is 3 times 96? Okay, 288. Multiplied by n squared plus 2n plus 1. This is 6n, that's fine, so I only have plus 64 and 2n squared plus 3n plus 1. This one has 2n, so it needs a 3. So 3 times 28, 84. I still ran out of room. So do I write it here? I'm going to write it here. So it's 84 n plus 1. And this one needs to be multiplied by 6n. So plus 12n squared. So these two should have been in here. But of course, I ran out of room. Okay, we are close. Almost there. So then equals limit as n approaches infinity 4 over 6n squared. Okay, 288n squared plus 288 times 2, 576, n plus 288 plus 64 times 2, 128, n squared, plus 64 times 3, 192, n plus 64, plus 84, n squared, plus 84, plus 12n squared. My goodness. Okay, so now I'm going to add the terms with n squared, and I only see, I see 4. Okay, so I have 288, and then plus 128, plus 84, and plus 12. 512. n squared. Now I want these terms. Okay, 576 plus 192, 768. And now I have these terms, 288 plus 64 and plus 84, 436. Keep an eye on my numbers, please. Okay, so from here we know that this is infinity over infinity. When we differentiate, you know what happens is the same degree over same degree. So it will be 4 times 512 divided by 6. So is 512 divisible by 6? No. Okay. Is 512 divisible by, no, by 3. Yeah, it is divisible by 3. But then, how come it's not divisible? Okay, 512 times 4 divided by 6. Am I getting 512? Yes, I'm getting 512. Oh, it's not divisible by 3. That's what I thought. Okay. So I can only divide by 2. So I get 10 to 4 over 3. So this is the exact area. Did you need me to explain from here? So we differentiate. We get 512 times 2 over 6 times 2. Then this will disappear, and then we still have same. 4 times 512 over 6. Do you need me to show this again with L'Hopital's rule?
Yes, please.
Sure. So
Would we be allowed to use that shortcut?
yes, because this is from pre-calculus. We know that when the leading coefficient in the leading, I mean the same degree over same degree is the leading coefficient over the leading coefficient. We know this from pre-calculus, but that's okay. Let's show. So limit Sn approaches infinity. I'll simplify by 2 and put 2/3 outside. I don't care for 2/3. So when I differentiate the top, I get 1024n plus 768. I differentiate the denominator, I get 2n. I still get infinity over infinity. So this is 2/3. Limit Sn approaches infinity. The top is 1024. The denominator is 2. So this is it. 2/3 times 1024 over 2. And I 1024 over 3. That's with L'Hopital's rule.
Thank you.
Sure. But now we want to, the moment of truth, we want to determine, as I showed last time, and this is where we will continue from.